All right, good morning everyone. I'm Dustin Price. Along with me is Ethan O'Hare, Andrew Hendrickson, and Jonathan Baker. We're here with Next Step Solutions to present the energy harvesting tile. So today we'll be going over the goals of our project that we set at the beginning, the entire mechanism design process, the building process, the testing that we did for this semester, the circuitry and testing we did with the circuitry, the Arduino and the testing that happened with that, and then what we should have done, and then we'll wrap it up with a summary. So for our goals, the overarching goal of the whole project was to convert kinetic energy into potential electric energy. And then by doing so, we will be able to count the footsteps that were used to create this energy, and then record and transfer this energy information via Bluetooth to an outside source such as a computer or to a phone device. Finally, we were to take this energy stored into a battery and power a small appliance. In this case, we powered a small 5-watt LED light bulb. Some of our design constraints included, for our economic constraints, we had that we must make the tile cost effective to be a great alternative energy to traditional energy sources we have currently. The health and safety was also another concern that we had. We must not make it a tripping hazard for people will be walking on it, thousands of people a day, because there's 10,000 footsteps that was averaged in Chicago on a given day in the heavy foot traffic areas. So we don't want people to slip on it because that would be very dangerous, and then we also don't want people to trip when it depresses. You don't want a big gap, that way people don't trip and fall. And then we must have environmental concerns as far as it must be resistant to corrosion, so making the metal so it doesn't rust and things of that nature, and then waterproofing, because that will also go along with keeping it from rusting, and then making sure the electronics work in both the heat, the cold, the water, the rain, the hail, and stuff like that. So where was our inspiration? Originally it came from PaveGen, a company that has not yet released too much information about what they have, so it's very difficult to really get a basis of what we had. What we found out though is that PaveGen is pretty expensive, for they haven't released any pricing information, and from what we gathered, we weren't totally sure because they don't have drawings released, but it seemed that they use piezoelectric generators to produce their energy. Then they also use brushless motors, from what we saw, to create this energy. So we try to mimic this design through our design iterations and match what they have currently. So some of our process ideas, as you can see in the lower left-hand corner, first we used piezoelectric transducer. That would, you push down on the piezoelectric and it creates a voltage potential. That was our original idea to go with. Upon looking into it, it's very expensive to get piezos that are cost-effective, that can actually produce enough power to produce any significant output source. And then our next mechanism that we tried to use was the flashlight crankshaft mechanism, as you see in the next picture to the right. This idea we thought would be very useful, but our first problem we ran into is we needed to convert linear motion into the rotational motion, and this directly converts rotational motion to rotational motion. So this wasn't an ideal first step to go towards. And then finally, one of our key takeaways that I had was I was walking through the store one day and I happened to see a salad spinner, and I was like, what more perfect way than already designed system that converts linear to rotational motion. So we bought one of those, we reverse engineered it, and we tried to go with that mechanism. And then the one thing that stayed consistent throughout the whole process was we used electromagnetic generation to produce our power via DC brushless motors. So our salad spinner design had some advantages and disadvantages. Some of the advantages were that it was simple in theory. You just push it down, the auger spins it, and it creates the rotational motion. And this also has been previously proven, so that was another advantage. We had a physical component right in front of us to replicate. Some of the disadvantages though was it was absolute manufacturing nightmare. To get the auger to have consistent rotations within, and then also to get it to have a low enough or a high enough rotation per centimeter was way too difficult for our design. So I'll pass it on to Ethan to tell about the things we've learned and continue on.
Thank you. As Dustin mentioned, we decided to abandon the concept of an auger to rotational mechanism due to the manufacturing nightmare in favor of a more simplistic approach. And this is a key career takeaway for us, that we need to know when to move on from an idea, when it won't be feasible to carry forward. And we also learned that manufacturing simple shapes, such as an auger, with the tools we had available to us in the manufacturing lab, was just not a feasible option. We couldn't get the tolerances we needed or the small size and the helical shape. Our only option was to heat up a small piece of aluminum and bend it, and we weren't able to get something that would be feasible to work with. So we decided to move back to the flashlight mechanism. It's kind of a rack and pinion pie gear that's a slice of a larger gear that, when depressed, turns a smaller gear that is attached to a larger gear on a clutch. And it was much easier to manufacture as there were no actual machine parts other than the axles. Everything was, or most of the parts were pre-made. We used Lexan plastic for the outside portion, and then we had metal L brackets to affix it to our tile. This also has the potential to produce much more power due to its higher gear ratio of approximately 360 to 1, which is not directly indicative of the power output, but was a rough estimate when designing. Our design for this was finalized on March 30th, and we started manufacturing on April 4th, which kind of means we're still in the test phase right now. We're kind of at a prototype point, which, if we had more time, we feel that we would have had a much more polished product, but in the short time we feel like we've made a lot of progress. Our housing is made of treated wood. The top portion right here has a stained waterproof finish, and the sides over here have a gray paint that is also waterproof. We do not actually have this top central portion of the tile finished yet. We're hoping to have either a neoprene or a carpeted finish on the top to prevent tripping and to increase the waterproofing. The tile itself is very stable. We have had almost all of our group members walk across it at about the same time, and there were no visible signs of wear and tear, no noises, and it was very stable. We also used wood putty as gap filler, as some of our 45-degree cuts weren't exactly at 45 degrees. For mechanical testing, the first thing that we did was we placed a 50-pound weight on the tile to test if it would actuate, and it got to about 80 to 90% of actuation distance, which the bottom 10% is where the button is, and we're confident with the actual impulse force of a step, it would actuate fully, but we were just placing it on there, so it wasn't the full momentum of an actual step. So we're confident a child and toddler would be able to activate the tile and produce energy. Our second test that we performed was placing approximately 500 pounds on the tile, on the central portion of the tile, and there was no sign of any wear or tear, no noises, just as previous. And this shows that it can withstand normal walking forces from anyone on the street. Mechanical testing for weather. We didn't actually perform any weather testing because most of our circuitry was still exposed, and we didn't want to risk frying our Arduino or any of our shields just because we wanted it to be waterproof. And it's still in the prototyping phase. So when it would be available for commercial use in its weatherproof stage, we would likely have it made out of sheet metal or forged or pressed or something along those lines. And the tile was able to perform in a hot environment of the senior design lab at approximately 85 degrees Fahrenheit. And we're reasonably confident it will be able to perform in colder temperatures as well. So we'll hand it off to Andrew for circuitry.
All right, so going on to the circuitry, our initial goal, our overarching goal was to use the signal that we got from the generators to be able to charge our batteries. Unfortunately, at the beginning, we really didn't have any idea of what the signal was actually going to look like. We knew that it would be some sort of voltage spike, but we didn't know how wide or how tall it would be. So our initial idea that we wanted to go with was to use a solar charge controller, because they have fairly similar applications. The solar charge controller also takes varied voltages and converts them to be able to charge a battery, and also deals with powering the load. So it was basically everything that we needed in one full system. Unfortunately, when we tried to use the charge controller in our applications, it was incredibly inefficient, and any signal that we got out of the charge controller was way too small to be able to use for anything. So at this point, we had a few problems. We needed to minimize the amount of hardware that we used so that we would actually have as much of a signal as we could, while at the same time keep within budget, because at this point we had used up a very large amount of our budget and we didn't have much left. So we chose to directly use just rechargeable battery banks, like the kind that you would use to power your cell phone. The advantages to the battery banks are that they have built-in overcharge protection. They're made to not charge all like overcharge, so it's a lot they also store enough power to be able to power our light for the amount of time that's required in the SDRD. We were also able to just directly plug our Arduino into one of them, and it was able to power the Arduino fully. So we know that as long as the battery is charging, the Arduino will be able to power the system. And they were also within budget. That was the main concern that we had. Unfortunately, using these batteries, we weren't able to fulfill some of the smaller requirements. Number one, we couldn't really read the level of the battery because it just outputted 5 volts. And they weren't really rated for extreme temperatures, extreme hot or cold. So without any type of insulation, we can't really expect this type of thing to be an outdoor system. When we first tested out the circuitry, we basically just took one of the mechanisms and one of the motors, and we manually pressed it to see what kind of signal that we would get. And here we were able to reach about 8 volts, and we tested the battery and found that it took about 4.5 volts to be able to actually start fully charging. And we did get about 4.5 volts for around 0.4 seconds. And that was our goal in the beginning, was to have about half a second per footstep charge. So it looked promising in the beginning, but unfortunately when we mounted all the systems and put everything together, the motor obviously became a lot harder to turn because all of the components were wired to it, and the mechanism was not able to spin the motors effectively at all. The braking torque was way too high. So it took a whole lot of force to be able to spin the motors, if at all. And because of this, we chose not to mount all the motors all together and then put the tile together and try to step on it, because we figured that if that were to occur, we would basically turn out to be a catastrophic failure. All of the mechanisms would most likely break with that very large force being stepped down. And that was a big takeaway for us, because we learned that you really have to think about what you're doing before you do it. And like, we know that if we would have done that instead of doing what we did now, we would have had a lot more problems now than we had before. And then just a few test results from the circuitry. We were supposed to have the motors be able to charge the batteries, but unfortunately, because of our stipulations from before, we didn't actually get to doing that. But conceptually, from the push down that we tested, it is actually possible to do it. Also, we were supposed to test whether the capacity of our batteries was able to power our load, and it was able to power our load for 8 hours from full charge with all 3 of the batteries powering the light. And I'll pass it off to John for the software.
Alright, so one of our goals was to be able to count footsteps, and that would be used to analyze and track pedestrian foot traffic. So our initial plan for that was to use an Arduino system to count these footsteps and store them within the tile. So the hardware we originally wanted to use was the Arduino Uno. However, once we started programming that system, we found that we didn't have enough memory on the board to store our entire program. So we switched to the Arduino Mega. In addition to that, we needed a few shields. We had a SD card shield, to store all of our timestamps. We had an RTC, real-time clock, which would be able to keep track of time whether or not the Arduino even had power. And we had a Bluetooth shield, which would be used to send any stored information to a mobile device, which has Red Bear Lab, the Bluetooth manufacturers, Bluetooth low energy controller application. So in terms of power and detection, our device, as Andrew said, is powered by one of our battery banks via USB. Footstep detection has a push button, which you can see right there. And on top of it, we have some insulation so that when the tile is fully compressed, we don't risk breaking the push button or damaging it. So when the push button is pressed, we detect a rising edge. And when we find that, we throw an interrupt, raise a flag, and the device will get our current time from our real-time clock and store it in a timestamp, which you can see there, which has month, day, year, hour, and then day of the week, which we use in our analysis functions. We also have a 400 millisecond delay so that when the tile is compressed, we don't need to worry about more than one footstep being recorded. So sending the information, our original design, we wanted to send the whole file. If we could send the whole file, we'd be able to throw it into an Excel document and do whatever we wanted with that. Unfortunately, with Bluetooth, that isn't really possible, so we had to make do with the developer's app and libraries and just see what we could do with that. And one takeaway from this is that you can't always get a perfect system. You need to sometimes compromise and make do with what's available. So we designed a system based off of a chat app, which was pretty much just your mobile device could communicate with the Arduino could communicate back. So we created a command prompt, basically, where you could send it specific commands and it would send back information after doing analysis of the onboard data. And one thing that we could have improved would have been a better app. You can see that it's somewhat random and when it's cutting off our text. And overall, if we could have designed our own app, we could have made the interface much better. So for the actual onboard analysis, what we have is we have a whole bunch of commands. We can manually set the time of the RTC. We can clear the data if it's getting too full. We can record daily and hourly averages and peaks, and what I mean by peaks is if you input a certain range, it'll tell you what time had the most footsteps, what hour of the day, or what day of the week. And we can also lock the device so that people can't access it without a password. So the reason we lock the device is because pedestrian traffic could be sold to advertisers or realtors. It's information that serves a purpose, and it can really be used to determine how well a storefront or a billboard ad would be seen. And not only that, but based on some of our commands, malicious users could set the date, set the time incorrectly, or clear our data. So when we tested our software, we found that stepping on the tile 50 times resulted in 45 timestamps, and some causes of that could be the 0.4 millisecond delay, or 400 millisecond delay. Or the button might not be getting fully compressed when we're stepping on the tile. And with the RTC synced, unlike our demonstration, we were able to accurately predict the hour. And statistical functions, we were able to verify by hand, just doing some calculations. And the level of the battery, as Andrew said, was unable to be tested and returned by the Arduino.
Okay, so if we could change some things, this would be our ideal final product. We would have 4 working mechanisms with the 2 printed gears we had and then the 2 purchased gears we had, making a 360 to 1 effective gear ratio. We would ideally make these out of metal and have a shaft integrated within them to keep it more sturdy and be straighter and more aligned. We would have 4 6-volt 5-to-1 motors or generators to power it, because those were the easiest to turn. Those were the ones that were actually getting us a reasonable result. We would have 4 rechargeable batteries with charge controllers integrated into them, and we would have 1 5-watt LED as we currently have. We would make the housing out of metal, so it was better for waterproofing and keep it sturdy. And then finally we would cast or make the supports out of metal in some sort of way to provide better support, and we could have better tolerancing within our holes that we made for the shaft supports. So in summary, we went over the goals. We talked about our entire mechanism design process, the build process, the testing we did this semester, the circuitry and the testing we did with that, the Arduino and that testing, and then finally we went over what we would have done if we could have changed some things. Are there any questions? Yes.
You went over what you would have done there. How would you have implemented that into your project sequence? So looking back, you can kind of see there's difficult areas. Is there a way you could have addressed those a little bit earlier, and how would you have gone about addressing them maybe to come to a quicker resolution that you might have trouble with the saddle spinning device?
Okay, so the question was kind of how we would go back and address the problem sooner, and then what we would do about addressing these issues. So I think a big thing is we had an idea and we were kind of afraid to leave that idea. So one of the big things is definitely when you see it's not going to work, leave it. Like, just be willing to throw it aside and start new, because we had this kind of alternative idea in mind the entire time, but we just were I don't know, we had to put our pride to the side to actually like let go of it. So definitely being willing to accept like a defeat in a certain area sooner, so that way you can move on from it and gain from your experience. That would definitely be something to do, and would have helped us quite a bit, because then it would give us more time on the back end to complete the process and be able to improve it much better.
So I agree with you, like setting this, like being able to move on is really important. What struggles did you have coming to that decision? What was holding you back from moving on a little bit earlier in the process?
So the question is like what was holding us back from moving on earlier? To answer, it'd probably be the fact that we already had a design in place. We saw that it was working with the salad spinner, and so we were confident that it does work in theory. And the other idea, we didn't really necessarily have an example to work off of. So I think just having that security of knowing there is something working out there that we could kind of lean on and have as a proof that it would work. So I think just the lack of proof that the other device would work was what prevented us from moving forward earlier. Any other questions? Yes.
Did you ever give it, so throughout the whole process, somebody steps on something, and then a motor turns, then you go through the charge controller, then power goes to a battery. There's an efficiency loss for each of those different processes. I think you said that you were able to get it on a bench top, pushing down with your hand and getting the motor to spin and getting everything there, right?
Mm-hmm.
So the question, you don't have to repeat all that.
Okay.
But how many joules do you get, like at the battery? So you push this thing down, and how many joules do you get for each push at the end of the line?
I don't remember, the question was how many joules that we get exactly. I don't remember the exact calculations. All I remember is calculating that we needed to be at the level of, at the point where we can charge the battery for at least half of a second. Yeah, that was we did all the calculations, and that was our conclusion, is that because of how many steps would be in Chicago on average, we needed to step on the tile for half of a second and charge the battery for half of a second per step in order to be able to get the power that we needed. I don't remember the exact number, but that was our conclusion that we came to.
That's a calculation. So
yeah,
what I was wondering is, at some point there should have been a scope on the on the input, and then like a scope on the battery. So a scope on the battery to say, well, I had like quarter of a second, and I got a voltage of this high, and a current of this much. So you might not have done that exactly, but I'm wondering, is it a You get half a joule, you get 5 joules, 50 joules.
Yeah, I'm not really sure.
Any other questions? Thank you.